My name is Ye. I'm glad to present our paper, EMR-MSF, Self-Supervised Recurrent Monocular Synflow Exploiting Eco-Motion Rigidity. This is joint work with my supervisor, Masatoshi Okutomi from Tokyo Institute of Technology. Monocular synflow aims to estimate both the depth and 3D motion of each pixel from two consecutive monocular images. In recent years, there have been several self-supervised methods introduced for monocular synflow estimation, harnessing the potential of vast unlabeled data resources. These methods jointly estimate depth and pixel-wise 3D motion and train the network in a self-supervised manner. One limitation of these methods is that they do not fully utilize motion rigidity that pixel-wise 3D motion on the same rigid object should satisfy. This further hinders their potential for achieving better performance. Due to the existence of rotation, pixel-wise 3D motion is not always consistent in the same rigid region. On the other hand, within the same rigid area, pixel-wise SE3 motion should consistently align. This serves as a valuable cue for estimating pixel-wise SE3 motion, which has been exploited in related works like Raster 3D. However, it was originally designed within the context of supervised methods relying on RGB data. In this work, building up on the Rhapsody framework, we first propose a novel self-supervised method for monocular synflow estimation and employ carefully designed photometric and geometric losses for self-supervision. To enhance motion rigidity within large static areas, we introduce a novel eco-motion estimation module combined with soft mask estimation specially tailored for static background regions. We've implemented two places of modifications to the Rhapsody backbone. Our first modification involves the substitution of fixed depth input within a jointly learnable monocular depth network. The second modification involves the integration of a novel eco-motion aggregation module designed to infer eco-motion in addition to incorporating a rigidity soft mask that helps identify static regions. In the EMA module, we iteratively refine a mask embedding map using the ConvGRU unit, which is later decoded to produce a rigidity soft mask. This rigidity soft mask assigns a value between 0 and 1 to each pixel, indicating the probability of it being part of the static region. Finally, we compute the eco-motion by aggregating the estimated SE3 motion field using the learned soft mask. Our network can be trained in a self-supervised manner, primarily employing view synthesis. Stereo images are only incorporated during the training stage, as in previous methods. Our view synthesis-based losses functions encompasses three key components: the temporal photometric loss, spatial photometric loss, and geometric loss. We utilize both the inferred non-occluding mask and an outlier mask to exclude invalid pixels from loss calculation. To explicitly enhance motion rigidity within large static areas, we introduced two additional loss functions. The SE3 motion consistency loss enforces coherence between the estimated eco-motion and pixel-wise SE3 motion within the rigidity soft mask. We introduced the mask regularization loss to enhance the precision of the learned soft mask in pinpointing static regions, as demonstrated in the visualization. In the KT synflow benchmark, our method outperformed prior self-supervised methods by a large margin. We achieved a remarkable 44% enhancement in the synflow all metric compared to the previous state-of-the-art self-supervised method. Our method even surpasses MonoSF, a hybrid method that combines supervised depth learning and energy minimization techniques. In scenarios featuring duplicated structures within static regions, our method demonstrates notably reduced errors when compared to previous approaches. This advantage is derived from our effective utilization of region rigidity within these static areas. In subtasks, including monocular depth estimation, visual altimetry, and optic flow prediction, our method consistently outperforms other self-supervised approaches, both those focused on single task and those designed for multitask learning. For more discussions and results, please check our poster and project page. Thank you.